Good morning, dear students. First of all, we'll start with your questions. I saw them in Google Chat, and I will answer after the practical lesson. I remember about you, don't worry. Today we're having the 11th practical lesson, line integrals of the first kind. So what is the difference between double or triple integrals that we integrate not by a region, 2D or 3D, but by the line? So I will explain you on the example. So the first task 1A, let's start solving. We have the following integral. So dl divided by x minus y and along the line L. So the L is a line segment, y equals 1 over 2x minus 2, and between points A and B. So let's plot this straight line first of all. So point A has coordinates 0, minus 2, and B has coordinates 4, 0. Okay, so 0, minus 2, A, and 4, 0, B. So we have to, so with so according to these points, we will define limits of integration. So as we can see from the graph, x changes from 0 to 4. This integral will be transformed to the definite integral. First of all, let's calculate dl. dl is, as you remember from definite integrals, that it is the differential of curve length, and it is calculated by the following formula when y depends on x. And in this case, 1 plus, so y prime equals 1 over 2. So 1 plus 1 over 4 dx, and it equals square root of 5 over 2 dx. Then I will substitute, instead of y, I will substitute this expression, and we will receive the following integral. So with limits of integration 0, 4. So instead, so dl is this expression, and x minus 1 over 2x plus 2. Let's simplify it a little bit. So I will move constants out of integral, and here I will have 1 over 2x plus 2. Yeah, and we also can multiply the denominator by 2. So I will receive, here will be square root of 5. Here x plus 4. And now we can integrate. So it will be so square root of a logarithm of x plus 4 with the substitutions from 0 to 4. And if I substitute, so I have a logarithm of 8 minus logarithm of 4. And actually, if I simplify it more, so 3 logarithm of 2 and 2 logarithms of 2. So the final answer is square root of 5 multiplied by logarithm of 2. Any questions about this exercise? Okay, I see that no questions. So let's move to the next exercise, exercise B. So we have the following integral. Okay, let's erase it. So 1b, the integral is the following. So along the straight, along the line L, x, y, dl. So as we can see, L is the contour of a rectangle with the vertices A, B, C, and D. So let's plot this rectangle. For 2 and 0, 2. And also let's make labels for them. So A, B, C, and D. Okay. So done with it. And also let's plot straight lines. So x equals 0, y equals 0, x equals 4, y equals 2. Yeah, and let's move everything up. And adjust different colors as well. Okay, let's go with green. So we have the following rectangle, and we need to integrate along this contour. So what do we have to do? Now we need to calculate line integrals on each segment separately. So what do we actually have? So we will split this integral into 4 integrals. So integral along AB, integral along BC, integral along CD, and integral along DA. So what about EAB? So if we integrate along AB, so x equals, oh stop, not x, y equals 0. If we substitute into the initial integral, we already can see that integral EAB will be equal 0. And now we continue to BC. So for BC, what do we have? So x equals 4. And what about DL actually? Yeah, so DL will be equal square root of yeah, so here x depends on y, so 1 plus 0, so dy, so it will be just equal dy. And the integral will be the following. So I BC equals okay, so x changes from yeah, by the way, x changes from oh stop, not x, but y changes from 0 to 2. So from 0 to 2, 4y dy. So it equals 2y square with the substitutions from 0 to 2. So it will be equal 8. Then segment CB. So here y equals 2. Then DL will be equal minus 1 plus 0 dx. Why we have minus here? Because we integrate from C to D, so inverse. And x changes from 0 to 4. Oh, yeah, from 0 to 4. And the integral will be the following. So what do we have here? So from 0 to 4 to x minus integral, by the way, from 4 to 0, because we integrate from C to D. So 2x dx. And now let's write down normal, so like more convenient limits of integration. And what do we have? X squared with substitutions from 0 to 4. So the result is 16. Yeah, and let's write down that it is integral I with index CD. Then dA. So it is quite simple. In this case, y equals 0. Oh, no, not y, but x equals 0. So integral, so I dA will be equal 0. So what do we have in the final answer? 8 plus 16. So integral equals 24. Any questions about this exercise?
Why always DL is 1 plus 0?
In this case, 1 plus 0. So because so here y is, so x is the function. So if we integrate along BC, x is a function that depends on y, but actually it is constant. And if I differentiate constant, I will receive 0. And in this case, the same. So differential of the curve length is the following: 1 plus y. So d.
Yeah, I
But
miss it. Thank you.
if we invert x and y, so just we'll swap the variables. So have I answered your question?
Yes, thank you.
Okay, more questions? Okay, if no questions, let's move to the next exercise. So exercise C, we have the following integral. So so the following integral, so dl, and we have square root in the denominator. And L is a line segment connecting points A with coordinates 0, 0, and B with the coordinates 1, 2. Let's put these points. So 0, 0, 0, and 1, 2. Actually, we can, yes, so we can see that it is the straight line y equals to x Of course, we can write down the equation of the straight line, but for now, let's go with the fastest solution. So L is such straight line. So x will be equal. So x changes from 0 to 1. And what about dl? So now y prime equals 2. So 1 plus 4. Square root of 1 plus 4 dx. So it is square root of 5 dx. And now let's substitute everything into the integral. So integral from 0 to 1. So in the numerator we have square root of 5 dx, and under the square root, so substitute 2x instead of y, so x square plus 4x square plus 4. Okay, so let's simplify it a little bit. So we have 5x square plus 4 under the square root. And now let's calculate this integral. So what do we have here actually? Yeah. Yeah, by the way, we can use also, we will use differential entry technique. So what do we have in the numerator? It is the differential of square root of 5x. So we have the one logarithm. So square root of 5x plus this square root, and with substitutions from 0 to 1. And what do we have here? So logarithm of square root of 5 plus 3 and minus logarithm of 2. And actually that's it. So calculated the integral. Any questions about this exercise? Stop. Here is a mistake. Sorry. Oh, no mistakes. Yeah, everything is okay. Yeah. So u and u square. Okay. Any questions?
Oh, no.
Okay, no questions. So let's move next to 1D. We have the following integral. So now line is more interesting. Yeah, by the way, rectangle is interesting as well. But now we have the arc of a parabola. So y dl, and L is arc of parabola. Y square equals x, and from point 0, 0 to point 1, 1. Actually, let we not waste time for plotting, and we will see it here. So this is the arc of a parabola along which we have to calculate the integral. So we can see that x changes from 0 to 1. And what about dl? Yeah, actually y equals square root of x. So for this segment, it will be square root of x. So if it was here, it would have been minus square root of x. And now let's calculate dl. So it will be equal 1 plus 1 over 4x dx. So it will be oh, okay. Yeah. So let me simplify it a little bit. So 4x plus 1, square root of 4x plus 1 over 4x dx. And now let's substitute everything into this equation. Oh, not equation, integral, sorry. So from 0 to 1, and square root of x multiplied by this square root dx. So what can we simplify here? We can eliminate square root of x. So it will be eliminated. It's not under the square root, okay. So eliminating square root of x and also moving 1 over 2 out of the integral sign. And we have the following integral. So let's calculate it with using differential entry technique. So we have so 1 over 8, and if so I do the following stuff. So I move 4x plus 1 under the differential sign. And now, so we have 1 over a multiplied by 2 over 3 and multiplied by this expression. Yeah, I will copy and paste and just erase d. And it will be enough. So with substitutions from 0 to 1. And what I here have actually 1 over 12. And here, so 5 square roots of 5 minus 1. And this is the final answer. Any questions about this exercise?
But why minus 1?
If I substitute 0 here, so square root of 1 multiplied by 1.
Yeah, I read. Can you scroll down a bit, please?
Yes, sure. Oh,
Thank you, no questions.
okay. Anybody else maybe has questions? Okay, if no questions, let's continue calculating line integrals. So the next task. So another case when we have the function given parametric in parametric form. So the following integral y square dl, and it is a quarter of the circle. X equals a cosine of t, y equals a sine of t, and t changes from 0 to p over 2. So actually this is it is the quarter of the circle that is in the first quarter. So t from p over 2, so this quarter of the circle. So, how to calculate this integral? As we remember from the integral of one, so integration of one function. So if we calculate differential of curve length that is given parametrically, we have the following formula. So square root of sum, so x prime square plus y prime square and dt. So let's differentiate these functions. So x equals minus a sine of t, y equals a cosine of t. Sorry, I forgot prime. Now everything is correct. So what do we have? A square sine square of t plus a square cosine square of t dt. And we actually will receive a dt. So this is the differential of length curve. And now writing down the integral, so instead of y, we substitute the expression for y. So, and limits of integration from 0 to p over 2. So, a square cosine, not cosine, but sine square of t, and multiplied by a dt. Let's move constants out of the integral sign. So a cube. Yeah, and how to simplify this integral, we already know. We will downgrade the power, reduce the power with using the following formula. So a multiplied by 1 over 2, and under the integral, we will have the following expression. So 1 minus cosine of 2t dt. And now let's integrate. So a cube over 2 and multiplied by so t minus 1 over 2 sine of 2t with substitutions from 0 to p over 2. So if I substitute p over 2 and 0 into sine of 2t, I will receive 0. And what is interesting for us, only t. So I substitute p over 2 and I have the following result. So a cube p divided by 4. And that's it. Any questions about this exercise?
Can you scroll down a little bit?
Yeah.
Okay, thank you. Everything's done.
Okay, so no questions, right?
Yes.
Okay, let's move next. So 1f. The next integral, we have the following integral. So 2 square root of y, integral from 2 square root of y, and L is the first arc of the cycloid. Now x equals a sine of t, and now, oh, stop, I look into e. Yeah, so a we have t minus sine of t, and y equals a multiplied by 1 minus cosine of t. Yeah, and by the way, t changes from 0 to 2p, but let we plot this curve. So a multiplied by t minus sine of t, and a multiplied by 1 minus cosine of t. And t changes from 0 to 2p. So it is the first arc of the cycloid. If I write down, for example, 4p, it will be, so we will receive two arcs of cycloid, but it will be enough only one. So according to condition, we need to integrate along the first arc of the cycloid. So again, calculating derivatives. So x prime equals a over 1 minus cosine of t. Y prime equals a sine of t. And now let's calculate dl. So a square 1 minus cosine of t square plus a square sine square of t dt. So now let's simplify this differential of the curve length. So let's move a out of the square root. So 1 plus 1 minus 2 cosine of t plus cosine square of t plus sine square of t dt. Okay, what can be simplified? So a by square root of 2 minus 2 cosine of t dt. Okay, so done with it for now, and let's see what we will receive here in this integral. So yeah, we will stop simplifying for now. So t changes from 0 to 2p, then square root of 2 and multiplied by this expression. And we actually have this expression. And if we can, as we can see, we can eliminate this square root. So we can simplify it. So what will we have here? So actually I can move a out of the square root of a out of brackets, a and the square root of a. So removing it here. And then, so these expressions are equal. So we have a rational integral. So we have the following expression. We will integrate the following expression. So everything is quite easy. So what do we have? 2a square root of a and multiplied by t minus sine of t from 0 to 2p. So sine will be 0, and what we have for p a square root of a. So this is the final answer. Any questions about this exercise?
Why y prime equals this value? Because like integrating, I think it must should be
But we differentiate y by t, so uh, uh, if I yeah, so okay, I can write in details. So actually, it will be a minus cosine of t prime. So a prime will be equal 0, and minus cosine will be minus cosine prime will be equal yeah, minus a cosine prime will be equal a sine a sine.
okay. Understand. Thank you.
Yeah, so
That is
just yeah, so
I see.
yeah,
Thank
so
you.
it is the derivative from table. Yeah, so don't forget that if you differentiate the cosine, the sign is changes. Okay, more questions? Okay, as no questions, let's go to the next exercise. What do we have here? So the last exercise from task number 1, we have the following integral. So x squared plus y squared dl, and it is the arc of the logarithmic spiral. So here we have polar coordinates. And let me remind you how to calculate dl in such cases. So rho square plus rho prime square d phi. So we have the following so the following differential of curve length. So rho square will be equal a square e in power of 6 phi. Then rho prime equals 3a e in power of 3 phi, and rho now stop hotkeys, yeah, confusing a little bit. Rho prime square will be equal 9a square e in power over 6 phi. So let's substitute these squares into under the square root. So what we have a square e in power 6 phi plus 9a square and e in power 6 phi. So what we will receive, actually it will be square root of 10 a and e in power over 3 e in power of 3 phi d phi. So calculated. And what about logarithmic spiral? Let's plot it. So from point A0 to point 0, 0. So actually we have the spiral has the following formula. By the way, let me check if it is so how it's solved here. Mhm. Ah, yeah, we also have improper integral in such case. But first of all, let we transform this expression under under the integral. So x equals, let me remind you, rho cosine over phi, and y equals rho rho sine over phi. So x square plus y square will be equal rho square. So we will have the following integral. So from yes, so rho square and multiplied by this stuff. And what about the limits of integration? So from a 0 to 0, 0. So actually, if a so if we have the point a0, phi is equal to 0. And what about point 0, 0? In such case, phi changes from so it changes, so it approaches to minus infinity in this case. And let we also invert limits of integration for our convenience and move constants out of the integrals. Yeah, by the way, instead of rho, what will we substitute? So it will be a square e in power over 6 phi. So what we substituted instead of rho, and here, so now let's simplify. So what I will move square root of 10 and a cube. And what about e? So it will be e in power over 9 phi d phi. So minus this stuff and multiplied by 1 over 9 e in power over 9 phi with the substitutions from minus infinity to 0. So if I substitute 0, I will receive 1, and if I substitute minus infinity, I will receive 0. So the final answer is the following. So minus this stuff. Okay, I will move 9 here. So this is the final answer. Any questions about this exercise?
No.
Okay, no questions. And for now, let we have a break for 5 minutes. And after that, we will solve tasks related to usage to the application of line integrals of the first kind. Okay, let's continue. So now we will solve tasks related to application of the line integral of the first kind, and actually the most logical thing is to so the first logical task on application of the line integral, it is to calculate the length of the curve. How it actually can be calculated, we just integrate dl along, so differential of the curve length that you actually know already from usage of the definite integral, and this line integral will be transformed to definite integral as well. So we have an interesting case. It is the helix given with the following equations for a cosine of t, y equals 4a sine of t, and z equals 380. Yeah, this curve is three-dimensional, but we can, yeah, we will plot just to understand how it looks. So we have the following helix, the following graph. So, but here, so for cosine of t, for sine of t, okay, let's put 3 here. So, and a will be equal to 1, and a here, a here. So the following, so actually it is the spiral. Okay, just for our understanding. And t changes from 0 to 2p. How to calculate differential of curve length? Analogical to two-dimensional case, but we also add z, z prime square. And everything is calculated analogically. So, what do we have here? For a square, 16a square, 16a square sine of t, sine square of t. Plus 16a square cosine square of t plus 9a square dt. So I just differentiated already here. So so how can we simplify it? So it will be easily simplified. So we have 16a plus 9a square, and the result will be 5a dt. So that's what we will have to integrate. So we will integrate actually constant. So integral from 0 to 2p dt. And it will be 10 a p. And that's it. So this is the length of the curve. Any questions about this exercise?
No questions.
No.
Okay, no questions. And now let's maybe skip this example for now, B. Maybe we'll return to it, but now let's move to D, to 3. So actually B is even easier than A because we have power functions and only 2 dimensions. So 3A. So here we need to find the mass of the material arc. If mu is a given density. How actually calculate the mass? So we need to calculate the forward integral. So we integrate mu from xy on this curve. In case A, L is the quarter of the ellipse, x square over 4 plus y square equals 1. So quarter of the ellipse line in the first quadrant. Let me plot it. So x square over 4 plus y square equals 1. And we need to integrate, so we need to calculate mass of this part of the ellipse. Yeah, I can just write down that x is not negative and y is not negative. So this curve. Okay, what next? The density equals, so at each point is equal to product of the coordinates of this point. So it equals xy. How to solve it? How to calculate? So yeah, so it will be equal the following integral, and I suggest to parameterize this curve. So it will be given, it can be given in parametric form. So x is equal to cosine of t, and y is equal sine of t. Then mu from xy, yeah, will be equal actually mu from t, and it will be equal to cosine of t, sine of t. Okay, and what about limits of integration? T it changes from 0 to p over 2. So it is better to integrate trigonometric functions that a lot of square roots. Yeah, and what about dl, of course? Let we not forget it. So dl will be equal, 4 sine square of t plus cosine square of t dt. And it will be equal, so 3 sine square of t plus 1 dt. Yeah, it will look a little bit complicated, but this integral will be calculated easily. So yeah, not obvious, but you will see. How can we simplify it? So we have the following stuff. Yeah, it looks complicated, but we will use differential entry technique. How we will use it? So we can simplify the following. So we can differentiate the following expression under the square root So if I differentiate this expression, I will receive 6 sine of t by cosine of t dt. So actually this stuff is similar to the differential of this expression. So we have 1 over 3 and the differential over this expression. So let's calculate this integral. So what do we have? 2 over 9 and this expression by the square root. And with substitutions from 0 to p over 2. So if I substitute p over 2 into the sign, so 1, okay, so let's calculate 2, so 2 over 9 and here, so 4, okay, so 4 by 2 minus 1, so it will be equal 14 over 9. Any questions about this exercise?
No questions.
Okay.
Why you apply this substitution for x and y? Particular this, I mean.
So you mean why I parameterize this function?
Yeah, I understand. This is constant.
I
yeah, no
don't
question.
want to integrate a lot of square roots. So x, y, so it will be 1 minus x square, so under the square root, so it is not really convenient. So, but we can easily simplify it. So if we integrate along ellipse or a circle, it is a good idea always to parameterize, move to polar coordinates. So actually, it is like moving to polar coordinates, but we have only one parameter t. So it's easier in such case.
Yeah, I understand. Thank you. I forgot about this.
Yeah. So good life hack. So use it. More questions? Okay, if no questions, let's move to the next task. Okay, I will skip B for now and let's move to C. So because B is, again, we have parametric function, but it looks easier. So what about 3C? So we have Bernoulli cascade. Oh yeah, I erased again the so I erased the formula, but nevertheless, so I will restore it. So integral of mu xy on dl. So mu xy dl. So formula is the following. So of the lemniscate, rho square equals a square cosine over 2 phi. And the density equals so k rho. Yeah, and let's also write down the so let's write down in the explicit form. So it will be k a and the square root of cosine over 2 phi. Now let me also calculate the dl. So rho square we already know, and what about rho? rho prime. Yeah, by the way, rho is the following expression, and rho prime will be equal a by 2 cosine of by square root of cosine of 2 phi. And multiplied by minus 2 sine of 2 phi. So it equals minus a over square root of cosine of 2 phi. And what about rho prime square? So it will be equal a square over cosine over 2 phi. Well, don't worry, everything will be simplified. So square roots will be eliminated. And now let's calculate the differential of curve length. So let me remind you the formula. So rho square plus rho square prime d phi. So it will be equal this stuff plus this. Let me expand. Okay, and let's see what can we simplify. I can move 8 out of brackets, first of all. And now, so, yeah, cosine square phi plus 1. Cosine square 2 phi plus 1 over cosine of 2 phi. Yeah, and lost d phi everywhere. It is not a good idea to lose. Okay, let's leave it for now, and we will see how can we simplify it in the integral. Yeah, and what about Bernoulli-Lemniscate? Yeah, first of all, let's assign limits of integration. Uh, a cosine of 2 theta. Yeah, only explicit form. And here I will have a square root. So we have the following figure. Yeah, so everything is taken into the consideration. So, yeah, by the way, yeah, we integrate from 0 to 2p. Let's substitute this stuff and this. Then I suggested to modify. Okay, well, first of all, let's eliminate this cosine. So square root of cosine of 2 phi. And move constants out of the integral sign. And now, so as we can see that this lemniscate is symmetric, so we can just integrate along this segment and multiply it by 4. So 4, and here we integrate from 0 to p over 2. Then what can we do here? Just a moment, let me remember it. So what I did here. Yeah, something here is not correct a little bit. Yeah, so my bad. I made a mistake. Yeah, I lost this sign. So here everything is incorrect. So sine square of 2phi. So here as well, sine square of 2phi. And here I need to multiply, so cosine square of 2phi plus sine square of 2phi, of course, will be such expression. But let we rewrite it in the following form. So a over this square root d phi. So it was a mistake here, but let we correct it, and it will be even simpler that it was before. So as we see, square roots are eliminated easily. And then we can also move k a square out of the integral sign. And now let's also use, so let's simplify with use, let's change the limits of integration. And the final answer will be 2p, oh, sorry, 2p k a square. Let me check here as well. Lost k here, so but here it is taken into consideration. So this is the final answer. Any questions about this exercise?
No.
Okay, no questions. Okay, let's also solve one more exercise, exercise 3b. Just because we can do it, we have some time for this. So we have, okay, so I will erase mass. And here we have three variables. Oh, it is mu xy, okay. So L has the following equations. So it's given by following equations. X equals AT, Y equals A over 2 T square, and Z equals A over 3 T cube. And the density is the following. So 2y over a. Okay, let's rewrite it as a function of t. So 2 over a and multiplied by this stuff. So it will be just equal t. So simplified. What is it? Sorry. Uh, I guess that somebody accidentally, or you wanted to ask to show something. Okay, let's clear all drawings for now. Okay. So done with this, with the writing down mu. And let's also plot this curve. So in this exercise, so AT, okay, let's add slider for T, or how it was here. AT, and then no, A over 2 T square, and A over 3 T cube. So not really not really understandable the limits of integration. Maybe we can see, maybe we can receive more information. So yeah, T from 0 to 1. Okay. So actually that's but we plotted the curve and how it equals. So from 0 to 1, such small segment. So curve in 3D. Actually, if the curve is given on in 3D and you have to integrate along such curve, it is also always must be parameterized. So T from 0 to 1. So what we will do next, we will write down actually the integral. No, we won't do it for now because we need to write down dl. X prime equals a, y prime equals at, and z prime equals at square. And now let's write down dl. So it is the following. So a square plus a square t square plus a square t in power of 4 dt. So let's move a out of brackets first of all. So what do we have? 1 plus t square plus t in power of 4. Dt. And that's a good question, how to simplify it now. Such irrationality. Yeah, so here everything is correct. Okay. Let's think. How can we do it? Yeah, so we cannot really. Okay, let's try to extract the perfect square. Maybe it will happen. Maybe it will be help somehow. So, yeah, it's not such a standard case. So what do we have? T square, okay, plus 2 multiplied by 1 over 2t, then plus 1 over 4 minus 1 over 4. So we have here t t square plus 1 over 2 in power of 2 dt. Yeah, let's verify. So t in power of 4 plus, yeah, it will be, and here, so 3 over 4. 3 over 4. And now what can we do now? So I guess we can use differential entry technique. So actually differential of this stuff will be equal differential of oh yeah, by the way, differential of this expression will be equal not really. No, we need to differentiate this, so it will equals to t dt. And now let's see what else can we do. Oh yeah. So now let's do a substitution, and then I guess we will be able to integrate by parts. So the substitution will be the following. So t squared plus 1 over 2 equals s. Then so when s equals so when t equals 0, then s will be equal to 1 over 2. When t equals 1, s equals 3 over 2. Okay. By the way, maybe we have such integral in the table. I will see.
We have, but I can't attach that. The lecture have sent us.
Oh,
I
uh-huh.
just found it.
Okay. Anyway, let's first of all rewrite the integral with new limits, and then we will just calculate the table integral. So s square and ds here. Okay, you can. By the way, cannot you attach in the chat? Because,
Yeah.
mm,
But I
everyone,
understand how it
so
is.
try to copy and paste here. It should work.
No, copy paste I can, but I can attach full file.
No, just print screen of this the integral. Yeah, because it's not so really it is quite a rare case when we have such integrals. So it's not really like a table integral. So we don't often use it. Yeah, but also I will Google it as well. Yeah, and by the way, as I understand, you have it in the in lectures as well. Mhm.
I sent
Oh, yeah,
lines. Yeah.
mhm. Thank you, Daniel. Yeah, so we will use this integral. So u square plus a square. So, okay, let's rewrite it. Let's calculate it. So a over 2 multiplied by the following integral. So in our case, we have 1 over 2. 1 over 2 square root of s square plus 3 over 4. Yeah, and s here. Plus plus 1 logarithm. Yeah, but 1 over 2 by 3 over 4 logarithm over this stuff. So s plus this square root. Phew. And now we can calculate it. From 1 over 2 to 3 over 2. Okay. So calculating a over 2. So if I substitute 3 over 2, so what I will receive? So 3 over 2, and here 3 over 4, 3 over 4, and here 3 over 2. And minus, okay, let's write down 1 over 4 here. Here 1 over 4 plus 1 over 2, and here 1 over 4. Okay. Let's leave it like this for now, because really a lot of calculations. So a lot of things that we need to simplify. So just arithmetical stuff. But the answer we found. Any questions about this exercise, the whole lesson, previous lessons? Yeah, I remember about your questions about individual tasks. I always answer, so don't worry and feel free to ask.
Yes, for now, no questions from me.
Okay, so have a nice day, stay safe, and goodbye. Thank you for your attention.
Thank you. Goodbye.
Thanks for the lesson. Have a nice day too.
Thanks.